for Lab 5, we wanted to look at the aberrations in a lens, specifically spherical aberrations in this lens. So what we set up here is what's called a Hartman filter. It's essentially 11 lines in a row, and that allows us to select different ray bundles. So, for example, right now, since it's at the very edge, only the marginal rays can pass through the mask to reach this lens. And so we know that only the marginal rays are making it through the system. Before the Hartman mask, we have this mirror going to the laser, and that basically just allowed us to make an easy translational motion to select which hole in the Hartman mask the beam went through. Now, behind the lens, we have a microscope that lets us find where those marginal rays are coming to focus by aligning the beam spot with the crosshairs as usual. So if we change where the beam's located, which will probably take too long, but let's say, hypothetically, that we put our beam in the center here, then only the paraxial rays would make it through the system, and so only the paraxial rays would make it back here, and we could find where they focus. And so we would move the microscope to find the difference in focus positions. Pause. We found the tangential and longitudinal ray plots. We flipped the lens around and found the tangential ray plots again, and compared the spherical aberration to determine which shape factor was better.
Okay, so this is transverse aberration. What we have is a laser coming through a mirror that we adjust up and down to pass rays through our Hartman mask and hit different points on the pupil, one of 11 different points. These points focus to the marginal focal point. We move our microscope objective up and down in order to see where the rays focus on this plane, and then we can get both our ray error and normalized pupil coordinates and plot our ray scan error. Okay, so this is longitudinal aberration. Basically what we had is rays from the outer part of the lens having higher power and focusing to marginal focus, rays near to axis focusing at paraxial focus. We focus our microscope objective from marginal focus to paraxial focus and get our longitudinal aberration.
We went and modeled our lens in Code 5, and here's the first orientation with a shape factor of -1. So we went to marginal focus, where the outside of the pupil has 0 aberration, and the max spherical aberration was about 300 microns. Then when we flip the lens around, we have a shape factor of +1, and here we see that the maximum spherical aberration is about 75 microns, cut down by a factor of 4. So with the plano surface towards the source, we measured the aberration, and we got this cubic shape, which is typical of spherical aberration, as well as a slope at the center. And this negative slope means that we're inside focus, which is exactly where we'd expect marginal focus to be. So then we flipped the lens around, and this is on the same scale as the last graph, so you can see that we had a lot less spherical aberration with the convex face towards the source, and it's about a factor of 3 less. And finally, we measured the longitudinal aberration. So we started at marginal focus and worked our way out towards paraxial focus for a difference of about 0.21 inches, and Code 5 estimated that we would get about 0.24.